Dear viewers, in this video I am going to explain you about how to trace the VMPP and IMPP, which is correspond to the maximum power point of the PV curve. So here it shows the voltage and current, the relationship of the photovoltaic cells. So this curve has two parts. So one is the constant current part. This is working at constant current, but whereas this is fairly a constant voltage. And these are the PV curve of the solar photovoltaic panel of 250 watt at different irradiance. The irradiance is varied from the 400 to 600, that is 2000 watts per meter square. So by changing with respect to the irradiance changes, we can see that the peak of the power curve is the moving up. So this is because of the changes in the photovoltaic current. But the short circuit, the open circuit voltage is almost same. So there is no the drastic difference in the open circuit voltage of the PV panel. So here we can see that the irradiance is mostly affecting the current, the photocurrent, but it is least influencing the open circuit voltage of the panel. And in this video, I am going to explain how to trace the peak point, the peak power point, the MPP point of the solar panel with a simple circuitry systems. So there are different type of MPP techniques are available in the literatures. So they are Petter band observe and hill climbing and incremental conductance and fractional short circuit current method and fractional open circuit voltage method. So these are the most common MPP techniques available in the literature. In this video I am going to explain you to the fractional open circuit voltage to trace this, the peak, the pinnacle of this PV curve. For obtaining the voltage and the power of the PV panel at different irradiance, I used the MATLAB the programmings. So here you can see that MATLAB M file. So with this file I developed the PV curve of the panel at different irradiance. So here you can see that this one represents the current and voltage, and whereas so this curve represents the power and voltage of the panel. So this tabular sheet shows the voltage and power of the PV panel at different irradiance level. So this one is corresponds to the 400 watts meter square, and this one is corresponds to 600 watts per meter square, and this one is 800 watts per meter square, and this one is for the 1000 watts per meter square. So here I highlighted the VMPP and PMPP with the blue color. So you can see that the maximum voltage and at which you can obtain the maximum power from the PV panel. So the green color represent the open circuit voltage. So open circuit voltage of the panel at 400 watts per meter square is 33.94, and similarly the open circuit voltage of the panel at 600, 800 and 1000 are 34, 35 and 35.52. So if you take the ratio of the VMBP and open circuit voltage of the panel at different irradiance, so it came to light that the ratio is almost same. So at 400 watts per meter square I got around 0.78, and at 600 this is around 0.78, and for 800 watts per meter square the ratio is 0.77, and for 1000 it is around 0.76. That means the value of the ratio between the VMPP and VOCC is between 76.76 and 0.78. So with this relationship we can easily obtain the peak of any solar panel. So this is the peak, this is the VOC. So this point is 0.78 times VOC. So with this relationship you can easily trace the peak of the PV curve. So I'm going to use this method to trace the peak value of the PV curve. Let's see that how we can do this with in a hardware system. So here we can see that a solar PV panel is there, and solar PV panel is directly connected to a switch. This is just a schematic diagram, and here we can see that a DC to DC converter and a load is connected across the converter, and the switch is open for every 10 minutes. That is a switching interval of this switch, because we need to measure what is the open circuit voltage. To open circuit voltage we need to open the switch, and we need to measure what is the voltage across the panel. At open circuit voltage the current should be 0. So how to make this current 0? Just by opening the switch the current becomes 0. So we can use this data, open circuit voltage, and we can multiply it with the K. K is, we discussed that 0.78 or 0.76. It's okay. Let us take K equal to 0.78. So when we multiply K and K with VOC, we will get the reference value of VMBP. Whereas this VPB represents, so what is the voltage across the panel when it is connected to the load. And this PI controller always try to bring this VPP close to VMBP. So there is an error is always generated by comparing VMBP and VPP, and which is feed to the PI converter. So PI controller, the PI controller always try to minimize or make this error 0 by bringing VPV close to VMBP. So this PI controller will generate the appropriate duty, the cycle for the DC to DC converter. So DC to DC converter always try to bring the external resistance is equal to internal resistance. This is the theorem behind the maximum power transfer theorem. So what is external resistance? So external resistance is the load resistance by the duty. So by changing the duty, the effective value of resistance seen from the input side we can control. So by matching the resistance of the internal and external, we can extract the maximum energy from the solar panel. So how do we extract the power? The line in the voltage and the current curve indicates the load line. So this is delta I by delta V. So if you take the inverse of that one, this is R. So this load line may be any point, but by changing the value of delta you can change the load line. If the load line exactly intersect this point, which represent V MPP and I MPP. This is the point at which the power is maximum. So this is the most easiest technique to implement MPP techniques. So here just one sensor is enough. That sensor is voltage sensor. So with the voltage sensor, measure the open circuit voltage and multiply it with the K. You can tune this K appropriately with any value of the temperature and irradiance. So whatever be the value of K is the fairly equal to 0.78 to 0.76. So if you multiply these two, you will get the reference value. So when you compare the reference value, the actual value of the voltage across the panel when it is connected to the load, which will produce a mirror, so that feed to the PA block. So PA block always try to make this error 0. This is the working principle of the fractional open circuit voltage control. For hardware implementation, we required one and a whole circuit because at least for 10 minutes this whole circuit need to store the value of VOC that get multiplied with the value of K. So when we implement this circuit using microcontroller techniques, so we need to use a whole circuit and a memory elements to store the VOC at least for some time. So here I selected the switching period is at 10 minutes. So at least for the next 10 minutes that the processor the controller need to store the value of open circuit voltage. So and you can reduce this time, as if you reduce this time, the switching frequency will increase. That means the more time the PV get disconnected from the load, that means that will impact the performance of this controller. So this 10 minutes is fairly a good approximation for closing and opening the switch. So I try this method to extract the maximum power from the PV panel with very simple methodology, and the sensor requirement is just one sensor is enough for implementing this method. So that is coming to the end of this discussion. So anything you want to learn more about this one, just drop your message in the comment section and subscribe my channel and share, and many similar videos are coming into this channel, and stay tuned.